So today we are going to learn about the master slave JK flip-flop. Let us directly go into the master slave configuration, and before that just want to highlight that the JK flip-flop, as you see in this circuit, can also be represented by the circuit in the right hand side. So this is simply breaking down the NAND 3 input NAND gate into a 2 input NAND gate and a 2 input AND gate. Okay, so this is very obvious. I hope you can understand this. And this actually, if you collect this part together, then this part is basically a SR flip flop, right? So it is the JK flip flop is basically the JK inputs coming to an AND gate, and another input of the AND gate is coming from the feedback of the outputs. Okay, so J is fed back from Q bar and K is fed back from Q. So they form the AND gate inputs, and whatever output coming out is fed to S and R. So it is like this. This is how we can also represent the JK flip flop using SR flip flops. So this is the same this diagram. So actually this will be useful, this particular drawing will be useful in the master slave configuration when we are analyzing the master slave configuration. Let us look at the master slave configuration. It is simply, you are basically tying up two JK flip flops, or for the matter of fact, if you look into the block diagram, this second picture, two SR flip flops you are connecting in series, and the JK input are coming to the input of the first SR flip flop, which is called the master SR flip flop. So SM and RM are denoted as the master SR inputs, and the feedback of this JK AND gates are coming from the actual output, which is the output of this second SR flip flop, which is the slave flip flop. So the outputs are denoted by QS and QS bar. So these are coming as feedback. Okay, so this is the configuration. The most important thing to note is that the clock is fed as a level triggered. Okay, it is fed as a level triggered. You can see that there is no triangle sign in this SR flip flops. Okay, no triangle sign is there. That means these SR flip flops are level triggered SR flip flops. Now this clock is coming here, that means this is positive level triggered or high level triggered. Now in here it is coming through an NOT gate, that means this is active low level triggered. So this is low level triggered. Okay, so this first the master is positive level triggered or active high level triggered, and this is negative level triggered or active low level triggered. So this thing you have to keep in mind when we are analyzing the circuit. So let us look into the circuit. So here we are having the circuit and we are trying to analyze the circuit. The analysis takes place in two steps. The first step is when the clock is high, when clock is 1. So when clock is 1, you can of course understand that the slave flip flop is deactivated, because this input is low. This input is 0 that time. Okay, so this is deactivated. So what does it mean? What it means that whatever was whatever output was there, it is basically had replicated this input QM bar, and it is QS and QS bar. It remains that, it does not change throughout this entire operation during high clock level. So QS bar does not change. So now let us go through the different inputs of J and K and try to see what happens to QM and QM bar. So only QM and QM bar will change. So let us see what changes are there for in QM and QM bar. But we also understand that to analyze QM bar, we have to actually assume what is QS and QS bar, because it comes and forms the SM and RM inputs along with J and K, right? So let us, so you see the truth table is divided in this way. So it is the clock 1 cycle, the high level cycle, and my QS and QS bar are 0 1. So when it is 0 1, this is the entire block which we are studying, and when it is 1 0, this is the block we are studying. Okay, now you have given JK inputs this. So for 0 0 JK input, what would be my SMRM when QS bar is 0 1? So you have to read it like this, and here you are reading like what is my SMRM input when QS bar is 1 0. So you can very well understand, since JK passes through an AND gate, JK being 0 0, SMRM will be 0 0 irrespective of what QS and QS bar is. That means QM bar will be memory state. Since SMRM is 0 0, QM bar is memory state for both these outputs. That means whatever QS and QS bar wire, it does not matter, QM bar will remain same, and just apply your thought that this memory is basically this 0 1, because QM bar being 0 1 would have given QS bar 0 1. So now I am saying that QM bar remains memory. That means it was 0 1 and it remains 0 1. Okay, so you must understand this. Here QM bar was 1 0 and now it remains 1 0. Okay, now you see when J and K is 0 1, then what happens? When J is 0, of course S becomes 0 irrespective of what. So you see SM is 0, SM is 0 here also. But what about RM? Because K is 1. So if K is 1, RM gets decided by QS, right? So QS being 0, RM is also 0. So here it is 0 0, and that means QM bar again remains memory. So in the occasion that we have supplied JK 0 1 and output means QS bar was 0 1, then SMRM is 0 0 and QM bar is memory. That means it is the same 0 1. But if my QS bar was 1 0, then SMRM becomes 0 1. SMRM becomes 0 1, and that changes QM bar to 0 1. QM bar changes to 0 1. When JK is 1 0, so I think I have highlighted all this like that. So okay, so when JK is 1 0, so now you see that K being 0, RM will become 0. But what about SM? So J is 1, so SM gets decided by QS bar. So in this case QS bar is 1, that means SM is 1, and that means SMRM being 1 0, QM bar will become 1 0. So when output is 0 1, QM bar becomes 1 0, and when output is 1 0, it is SMRM is 0 0 and QM bar is memory. That means it is same as 1 0. Now the next one, when we are supplying 1 1 to JK, then what happens? When we are supplying 1 1, that means SMRM gets decided by QS bar. So QS bar being 0 1 here, so it is 1 0 and QM bar is 1 0. QS bar being 1 0, SMRM becomes 0 1 and QM bar becomes 0 1. Okay, that means when we are supplying JK as 1 1, if the output was 0 1, QM bar becomes 1 0. If the output was 1 0, QM bar becomes 0 1. Okay, but now please understand these outputs are for QM bar, right? Not QS bar. But when we are studying the circuit as a whole, we need to understand what is the change in the output QS bar. Okay, but for clock equals to 1, this is not changing. This will change when clock is 0, and when clock is 0, the change is very direct. Whatever QM bar is, you will see that in QS bar. So this is what you see when clock is 0, whatever is QM bar, that comes to QS bar, right? So now we can combine these truth tables for the clock high and clock low. So the total clock cycle truth table is given here. So this is combined, this truth table is combined to give the truth table here. What we are trying to understand, in the total clock cycle, what is the change that we are seeing in the output, which is QS bar. So by looking at this truth table, we can see that when JK is 0 0, when JK is 0 0, then QM bar is memory. That means QS bar is also memory. It remains same. So no matter what is QS bar, your QS plus and QS bar plus will become memory. Okay, and this change happens at clock equals to 0, when clock becomes active low. When clock becomes low, then the change in the output of the slave happens. Now when JK is 0 1, then what we saw, that if QS bar is 0 1, then QM bar is memory. That means it is 0 1. So the output QS bar plus will also be 0 1. And if the QS bar was 1 0, then QM bar becomes 0 1, and QS bar plus also becomes 0 1 when clock is 0. Similarly, when JK is 1 0, then you find that for QS bar 0 1, QM bar becomes 1 0, and in the clock equals to 0, clock equals to 0 means when clock is low, this 1 0 comes to the output QS bar, and it makes it 1 0. But if QS bar was 1 0, then QM bar is memory. If QS bar was 1 0, then QM bar is memory, and it remains 1 0, the output. And when JK is 1 1, then QS bar being 0 1 makes QM bar 1 0 when clock is high, and when clock is low, this 1 0 comes to the output. And if QS bar was 1 0, then the output QM bar becomes 0 1, and when clock is low, this 0 1 comes to the output, and it makes it 0 1. So you can read the entire truth table. If you just ignore this column, this is what the truth table is reading like. When JK is 0 0, no matter what the output is, it remains memory. When JK is 0 1, the output you see is 0 1. When JK is 1 0, the output you see is 1 0. When JK is 1 1, the output you see, if it is 0 1, it is 1 0. If it is 1 0, it is 0 1. That means it is a toggle output. It is Q bar. So this is what you can see now. So the first JK 0 0 is memory state, 0 1 is reset state, 1 0 is set state, and 1 1 is toggle state. So this is what the exact truth table of the JK flip-flop was. So what did we achieve by connecting two flip-flops? So we are again coming to the same JK flip-flop truth table. So what did we achieve? We achieved this thing. We effectively created a JK flip-flop with negative edge trigger using level triggering of clock signal. I hope you maybe you have missed this, but just note, when does the output change? Try to understand this. When does the output change? The slave output change. The slave output changes at the instant when clock becomes 0 from 1. It does not change before that, right? It does not change before that, and it changes only then. It changes only then, and it does not change anymore throughout the entire clock equals to 0 level. It does not change anymore because the QM bar does not change when clock is equals to 0. When clock is 1, then QM bar will change again, and that change will get affected at the slave at the instant when clock is becoming low from high. So effectively your change in the output is getting triggered at the negative edge trigger of the clock. So using two level triggered flip-flops, which are basically we always have to use level triggered because edge triggering is only a concept, but in practice we always have to maintain some level, and then the change will take place, and that is what we are doing here in master slave connection. But the master slave connection, what it does, that over the entire cycle what we are experiencing is that the QS bar output changes at the negative edge trigger of the clock. So thus we can obtain a very perfect synchronous clock operation, synchronous flip-flop operation. It is synchronized with the negative edge trigger of the clock. So that is the case with master slave JK flip-flop. So that is all with master slave JK flip-flop. And this is important because the analysis is a bit complex. It has two cycles, clock 1, clock 0, and then you have to combine these two cycles in order to come to the understanding of this final JK truth table and why it is getting triggered at the negative edge trigger of the clock. So that is all. Thank you for your attention.